So, first of all, what I would like to talk to you about is brief introducing what membranes are used to today in industry, and then I should say process industry, because it is process industry, the chemical engineering, which is really my field. And then I would like to give you a brief introduction for special 3 of what we can consider as functional polymeric material as a starter. So, there are some very good books about these studies here. Some of you may know that. And for some of you, the membranes in industry or in process industry may be well known. But I take the opportunity to also say a few words about that, because we emphasize different things, whether you are in the basic material science or you are in the engineering science. So a brief overview now for where we have membrane applications today. I will talk about gas, and there we have 3 very important applications that has been for a long time. That is the production of inert from air. That is basically air products. They have a large part of this market. So, as you can see here, now I'll come back to that, because just as important as the materials when you come to the applications and the engineering, that is, how are you making your modules, and how will the gas be flowing in these modules? And what is the most important here? Is it the permeability or is it the permeance? And things around that. So natural gas sweetening, that has also been on the market for almost the beginning of the 70s, because the natural gas, or then you get it at high pressures, and for the standard membranes, you will need this high pressure for the separation. So you need to produce it to high quality by removing the CO2, and for the transport you also want to remove the CO2, and likewise you would like to dry the gas by taking away the water. The recovery of VOC at terminals and boiler loadings, that is also a standard standard application today, and for the future it will probably also be used on the ships or tankers. Now we have another 4th application that has not been so usual for membranes, but it's very, very important as we more now look towards green energy. So upgrading of biogas, but that is produced at low pressures. So what is the best membranes, best materials to be used for that? Okay, previously the biogas also were produced at landfills. That is, in most countries not allowed anymore to take it from landfills, and it is very difficult to make high quality fuel from that because it's so highly mixed with nitrogen. So it should be dedicated reactors where you have the organic waste. Then The applications that we can see under development is illustrated here. We have at power plants, CO2 from flue gas, coal-fired natural gas-fired power plants, and that will be post-combustion then. These are standard and old plants at times. So it can be easily retrofitted at an existing plant. But it is then delivered at atmospheric pressure. And all of a sudden you have a different challenge than for the applications we have had for so many years, where you have had the gas produced at high pressures. This is the main challenge, and we cannot say that this is a fully matured technology yet, because of you have to find the right process parameters, the pressures, the temperatures, and such. And this, then we talk economy immediately when it comes to this. Then it is cement plants, CO2 from flue gas, post-combustion. This is more or less the same, but it's a huge difference between these here, because we talk membrane separation, and then it is very important how high is the composition of CO2 in your flue gas. At a standard coal-fired power plant, let's say you have around 10 to 13% of CO2. If you have a natural gas-fired power plant, you're down to 3 or 5. And this has immense impact on your separation when you are using membranes. Cement plants, then your raw material is calcium carbonate, and you also have the burning of your fuel, which again brings your concentration of CO2 up to approximately 16, 17 mol%. And this makes it easier, but I will also tell you what is the challenge then when it comes to the materials. Steel industry, blast furnace, that's a complete different story. Then you have CO2, CO, and you have hydrogen in mixtures. And it's a huge amount also here of CO2. So even though that we say that we will do carbon capture for the future due to the climate issues, okay, we can, as time goes, replace coal-fired power plants, for instance, by other type of energies, but we will still, and for foreseeable future, we will have the cement plants. We will, of course, have the steel industry, and the CO2 need to be captured. Then we need membranes, refineries, and hydrogen, very valuable gas that needs to be recovered. That was also one of the first applications with membranes. But today, we talk for all these applications, we talk economy. And the industrial partner will all ask you when you come and you try to tell them that it would be a good idea to look into and to develop more on membrane technology, they will ask, what does it cost? So then we have the hydrogen production from water-gas shift reaction. And and that is a standard reaction. Natural gas is very often the raw material for that, but you can also say that this is a precombustion, integrated gasification combined cycle. Okay, so you have a shift, the shift reaction, so you produce hydrogen and you produce CO2. But this is not an ideal world. So this is very, very seldom just the mixture of these two gases. So here also it's some cleanup that is needed, and then you have the separation properties of your membrane. So all this comes together in a very important question. Just one word about the production of pure oxygen. This is not polymers. That will be the future in the oxy-fuel combustion. It will be ceramic oxides, basically, but we should also remember that we are using the polymers for batteries, for production of energy. But air separation, extremely important. It is easy to produce high purity nitrogen, but it is difficult to produce high purity oxygen unless you are cooling it and liquefy it. So it burns down to, or it comes down to, that we need to have a combination of all this here. So some of us loves to dive into the details of the materials, of the membrane materials, and then we start measuring permeabilities, always then permeabilities. We need to have also, if you want to see your membranes applied in industry in the end, and I mean in as a separation unit in process industry, then it's very important to also be clear, very clear about the transport properties, physical properties of gases, their potential interactions with the materials, and not only the pure gases, because you have pollutions, you have components that can be detrimental to your material. You need to develop the right materials, because these gas volumes are huge. So it is very seldom sufficient to have a pressure dependent, only a pressure dependent separation based on permeability and selectivity. So today the research here goes on tailor-made, sophisticated materials. And I know that you will also have a presentation tomorrow by a previous colleague of mine that will talk about selective carriers or facilitated transport. But these membrane materials, which are going to be used in industry, they will very often be hybrid materials, and they can be combining organic, inorganic materials. The operational conditions must be very clearly communicated if you are going to design a membrane for a special type of separation. What are the limits, for instance, for the temperature range? You can't necessarily cool down to a membrane separation temperature around 30-40 degrees if the gas is delivered at above 100. So all these things will have a very high impact on what you end up with going for development. But certainly also you must, in addition to these these understandings of materials and the basic understanding of the mechanisms for separation, you must have a good engineering and modeling. So when you design the process, this will always go hand in hand with modeling, with simulations going back and forth for your separation, because it can also end up that you choose the wrong design for your module. And if you don't have efficient flow of the gas, you will also not have an optimum separation. So based on this, it's very useful to go to the nature. And our lungs are excellent membranes, as we know, and in the transport of CO2 through the lungs, the enzyme carbonic anhydrase will help to transport the CO2 as bicarbonate through the lung membrane. So carrier-mediated transport for separation of gases using membranes will be trying to mimic this process here. So typical examples: development of functional polymeric hybrid materials will be for post-combustion. CO2 will be removal from biogas, which will supply green energy and will be recovering hydrogen from gas streams. So in brief then, the membrane will separate on basis on the molecules, the physical properties of the gases. So this is very often the membrane material properties are of course at the center, in focus, when a group of people, I guess like you attending here, they are very deep into this. For us, with the other leg strongly placed in the engineering part, we also have to look at the process conditions, temperature, pressure, concentrations. And the facilitated membrane will, of course, be needed also with water. So this may be or will be looking very basic to you, and it is basic, but my reason for putting up this equation is that it is a reminder of that the P, the permeability, is an intrinsic material property. We will start there, but what is of interest once you go into the process is the permeance. And the L here, as you know, will be the thickness of the membrane, but it is the permeability divided by the thickness of the membrane that is at focus when you go to compare membranes for a specific process, for a specific separation. And this will be what the industry will ask you about. Then another term of this equation is, of course, the driving force. This is the standard solution diffusion transport. And the driving force expressed as difference in partial pressure on feed side and on permeate side will always represent economy of the process. And this is where also the industry will say, do I have to compress my gas, or how can we do this? Well, we can set up a process and use vacuum to a certain extent on the low pressure side. And that means also that we are not handling the whole feed stream, we are handling the permeate stream. So we need something extra in this here, and when I present facilitated transport membrane on a few slides, you will see what I mean. Okay, let me go quick then. The ideal selectivity is again the basic what we measure, but we are interested in the gas mixture. The process selectivity, because we know that the different gases may influence and change your material. So we refer to the selective layer when we talk about permeability, but we are actually interested in the overall permeance of the membrane. Okay, depending on the design you have, the most used membrane modules are the flat sheets where you have the membrane envelope and you have this spacer between. So the gas is fed on the outside, as you know, and it will flow through the membrane and into the, as we call it here, the filtrate flow. The permeate. It can have fairly high packing density, this here, square meters per cubic volume of the module. And what should also be mentioned, you will know that the polymers are characterized by a TG. So that will also be important for the applications. Are they rubbery or are they at a state of glassy? And the rubbery materials are usually and can be easily be used in these type of spiral wound modules, while the glassy materials are usually hollow fibers. This is important for the company, depending on the volume, what type of module you then choose. Will it be large volume? You very often will use an outside in the side. The gas is fed on the outside of the fibers and your permeate can be taken out. They go into the fibers. So typically, if this is methane, for instance, or natural gas, fed on the outside, large volume, then the CO2 should go into the fibers. The air, when you produce high purity nitrogen, is usually fed on the inside. But the question is here, it's the pressure loss. How large is the pressure loss? So when you want to do natural gas sweetening, you focus on that you don't want to have so high pressure loss. So you will let the CO2 go inside the fibers. So all these things here are extremely important. And again, we talk economy. So the membrane that we have had success with for very many years, that was the facilitated transport membrane. Some combines actually two mechanisms. First of all, this was the standard driving force we have here, that's Fick's law, as you know, and it's the solution diffusion mechanisms. Now, when you have a facilitated transport membrane. You have help of a so-called carriers. And this carrier may be fixed, or it may just be embedded somehow in your polymer, or it may be, if it was a liquid, it would be a mobile carrier. So this is then a kind of membrane where you will have carriers fixed. So you have the two mechanisms at the same time. You have the solution diffusion and you have the facilitated transport. So now, if you have water present, just like you have humidity in your lungs, that CO2 will be quickly transported as a bicarbonate in the wet membrane, and it is attributed to a carrier. We used the polyvinyl amine. It has a lot that you have to purify, you have to do a lot of things to this here, and it's very important that you get it in the right form. Anyhow, you can see then illustrated here that the CO2 will both go through by solution diffusion, and it will be carried through the membrane by this reaction, by the facilitated transport. We were able to document this by looking at or measuring the flux as a parameter of the driving force here. When you have the standard solution diffusion, you will have a more or less linear line here. So for this measurements, we used a temperature of 34 degrees and a feed pressure of 1.5 bar. And we then had a change in the permeate pressure, which made us have an increase in driving force. And as you can see here, when the driving force is not so high, the facilitated transport will be dominating. As we go up we go to higher driving force, and we have a larger pressure difference. The solution diffusion may take more and more over, and you don't want to go to the place where the carriers are all saturated. You want to find the right conditions where the facilitated transport with a fixed site carrier effect is dominating. But this is not the only parameter here. It is also so that you have to prepare by the right pH, because you want to have it so that it is basic, so that the carriers are free as NH2, as amines. So we decided to go for pH 10 because it turned out that the support structure, which was polysulfone, was ruined if we went all the way to pH 12. Anyhow, this was tested at a coal-fired power plant where it was exposed to SOx and NOx and fly ash. Varying test conditions, temperature control failed, fallout of the desulfurization unit, flue gas desulfurization unit, and we could use an extraction point at a gas-gas heat exchanger here. Okay, the very good result was that the membrane could tolerate that. But this is just to underline Excuse me, I need to take a glass of water. To underline that these huge gas volumes demands excellent membrane materials and smart process solutions. Let's say you have 400,000 normal cubic meter per hour. So this may demand almost 600,000 square meter membrane area. So now you can start picturing how your module what your module should look like. If you have a cement plant and you want to use a facilitated transport membrane also there, then the flue gas also here is delivered at atmospheric pressure. So again, the facilitated transport membranes will be the best choice. I'm pretty sure of that. You will not need a dehumidifier of the gas stream, but you will need temperature control. You have high percentage of CO2 and your process is ready to go, actually. So this is an excellent place to use membrane. Cement industry, the volumes are not quite as large here, and waste incineration. With this, I go on to, I see I have approximately 10 minutes left. I will say a little bit about a very exciting project we had together with Rich Spontak and together with SINTEF in Oslo, where we looked at nanoparticles, POS nanoparticles, or should I call them molecules? I understand that there's a certain disagreement about that. The polyhedral oligomeric silces quizoxane. So the idea is that if you can replace the R group here with a amine, then we will expect the same carrier effect for CO2 through a polymer like a membrane with POS as we saw with a fixed site carrier membrane. So in this one here, I think we have 8 silicium atoms, so this would be a T8 cage then. A little more, this is a base based on the inorganic monomer R2SiO. It's a fascinating molecule which can have various structures, random or ladder or cage with different cage sizes, and this is indicated the number of Si atoms. I understood actually this from information from Spontak, that this also was introduced in General Electric back in 46. And later in Lichtenham and Schwab developed further these. And it started out by their attention to these materials when they were working in aerospace because of high heat resistance, it was strong and it was light. It's kind of fun to realize that if you replace the R2 with a methyl group, 2 methyl groups, you get the polymethylsiloxane, the silicane rubber, which is very well known and much used in membrane coating. It's a very stable and highly rubbery. So what happened to our project here? The POS structure were investigated for sustainability as suitability as carriers for the CO2. We used polyvinyl alcohol and POS in a flat sheet membrane, and we used PPO hollow fiber membranes and coated with POS. The cyclic capacity was of interest for us because we wanted to see how easily it would absorb and desorb the CO2. So 3 cage structures were studied, and these were synthesized by SINTEF in Oslo. So we had the amino, the amidino, and the lactamide POS. The amino, the amidino, and the lactamide POS here. We had very high expectations, but we also realized, or one should realize, that both carbonate and carbamate may form when you have CO2 and water present. So we don't want the high conversion to carbamate because it binds CO2 more strongly. And when we talk about cyclic capacity of these POS-containing membranes, it absorbs easily, but it also has to desorb. So if it doesn't desorb and carbamate doesn't desorb so easily, so in our studies here, we found that the amidino POS had the highest cyclic capacity due to the high conversion to bicarbonate, and it could say to be thus preferred. So I would say the advantages of POS is clearly the rigid cage structure, high thermal stability, relative high molecular weight, and tunable solubility reactivity. I have also seen referred to that the main producer is hybrid plastics. I'm not so familiar with that, but at least that is stated by Yavuz Kadamli. I think you are on the line here or attending. But we experienced that the POS in polymers did not show the expected carrier effect. It was difficult to document. We had the phase separation, we had agglomeration, and we had formation of crystalline segments. But I would say that it was very useful studies, but we find that it's still a way to go to obtain the desired carrier effect in the functionalized POS membrane. But the potential of these nanoparticles is clearly promising, but not necessarily as carriers in gas separation. Okay, 5 minutes, 3 minutes on the third membrane structure, which I will say is absolutely a functionalized material, because they are pore-tailed carbon materials, but you start by spinning the fibers, the hollow fibers, and then as we started by talking about, then you can end up with a bundle of fibers, for instance, for natural gas sweetening or for high hydrogen production. You can pyrolyze and you can get these carbon fibers. These are fairly, they can easily break, but we were able to make fairly large modules for demonstration of biogas. So the protocol, the carbonization procedure, is you have to kind of decide on that in each lab: temperature, heating rate, soak time, if you would do it under vacuum or use purge gas when you are pour tailoring the sizes here. And the fibers, for instance, the thickness of this carbon fiber is 16 micrometers produced in the lab. And you are in reality sitting having the skeleton of the polymer left when after you pyrolyze them. But the pores are slit-shaped, really. So this is what will also decide your separation efficiency. And the separation selectivity between methane and CO2 here can be as high as 60 or 80. It's very efficient for biogas, for instance. But again, then it comes to the module making. That is one of the challenges, and how that is prepared. You can pour tailor, you can add doping, some kind of doping, by functionalizing these carbons. And it's interesting here we have in the fibers, we added nitrates and oxides. And when you're pyrolyzing, you are burning off these gases, and you are left with a metal, which will enhance the separation, for instance, of CO2 here. So I'll speed up and finish off here. I think I have used my time. I had put up the process, typical process from the bioreactor to the production of high fuel quality methane. And we documented also then the recovery of methane was very high, and the VOB index, or the heating value, was above what was the goal for the upgraded biogas. And like we have, for instance, this process with when in steel production. This is also a fairly complicated process, but depending on what you are using here, pressure swing absorption, or you have an absorption process, then you can also replace it by membrane system. Facilitated transport if it is in favor of CO2, or by a carbon membrane in favor of hydrogen. Okay, so enough for that. The blast furnace here.
We're going to have to wrap it up because we're already over a minute here.
Yeah, okay. Then this is the last of this one and the summary. And then to you, Rich, congratulations. And to my very good friend Rich, and project, and as project companion over very many years. Thank you so much.